Welcome back to our second example. This one is a little different, as you can see. Again, we are given to solve this system of equation. The only difference in this one is that we have three variables and two equations. And so you probably will be asking, wait, I don't think you can find an answer to this, but yes, you can. And we're going to do that by the usual matrices. And so in our last video, we discussed like how to write, we were able to easily put this in matrix form. And so we're just going to go ahead and do that right away. So our A would be 1, 2, negative 4, then 5, negative 1, 2, multiplied by x, y, and z. And that is equal to our B, which is everything on the right. And so what we did after this is put this in an augmented matrix and then find our variables or find our unknowns by doing this in row or by putting it into row reduce echelon form. And so our augmented matrix, instead of a 3 by 3 this time, it would be a 2 by 3. So 2 rows, 3 columns. And so we're gonna have 1, 2, negative 4, 9, 5, negative 1, 2, and then 1, or 9, 1 on the right side. And so now what we're going to do is put this in row reduce echelon form. And so what we can do first is just simply eliminate the 5. So what we're going to do is we're going to multiply we're going to subtract row 2 by 5 times row 1, which would be our new row 2. And so that would give us 1, 2, negative 4, then 9. And so this will be 0. And then we'll have negative 1 minus 5 times 2, which would be 10. Minus 1 is negative 11. Or negative 10 minus 1 would be negative 11. And then negative 4 times negative 5 is 20. Plus 2 would be 22. And then 9 times 5 is 45 times negative 1. And then plus 1 would be negative 44. And this is really nice because the bottom part is all multiples of 11. So what we can do now is we can divide row 2 by negative 11. And so what we end up getting is the top row remains the same. The bottom row would be 1, 1, negative 2, and on the right side would be 9, 4. And then lastly, we could just get rid of this 2 simply by subtracting row 1 by twice the row 2. And this would be very convenient because our 0 over here won't affect this one, or this lone 1 on the top left. And so we're gonna do this simple calculation. So the bottom row remains the same, and then the top row we have our 1, so 0 minus, or 1 minus 0 is just 0. Then we have 2 minus 2, which would be 0. And then we have negative 4 minus negative 2 times 2, which would be 4 minus 4, and that would just be 0, which is kind of neat. And then lastly, we will have 4 minus, or not 4, 9 minus 4 times negative 2, and so that should be 9 minus 8, and will be 1. And so here is our row reduce echelon form. Like I mentioned before, our goal is to try to make it as, or turn it into this, ones across the diagonal. But as we can see here, we don't have a square matrix, so we don't have that 1 on the bottom row, or our last row, to give us our last one, and then eliminate the -2. So this is as simple as we can get it to be. So now what we're going to do here is we are going to write a solution. So if we were to put this back into our regular ax is equal to b, we will get 1 0 0 0 1 -2 multiplied by x, y, and z, and that is equal to 1 4. And so if we actually did the matrix multiplication, we will get x is equal to 1, and then y minus 2z is equal to 4. And so this is where the kernel comes in. So we mentioned before that the kernel is any vector y such that a times y is equal to 0. And it looks kind of weird because obviously the only way we can make this true is if y is just equal to 0. But there are other vectors that will satisfy this equation, and that's what happens in this case. So to find the kernel is we're gonna find or we're gonna move all the terms that are not what do you call it, do not have a constant of 1 to the right side. And so what that means is we are gonna change this, or x is equal to 1 stay the same, but the bottom part would be changed to y is equal to 4 plus 2z. And so when we write this in or when we write our solution in terms of a matrix, we will have our x, y, and z is equal to 1 4 0, because z here is we don't know, so it's just going to be 0 in this case, plus, so here is where the kernel comes in. So we're going to let this z equal to t, so where t is just some constant, and then what we end up getting is this portion here would be 4 plus 2t. And so what ends up happening is we can write this as t multiplied by 0 to t, not t, 1. And that would be our answer to this question. And so this makes sense because if we were to rewrite all this, I'm going to use a different color. It's going to be x is equal to 1, y minus 2, take that back, y is equal to 4 plus 2, we're going to substitute z with t, and then z is just equal to t. This part here is the same as this, because if we were to write this down and actually did the quick little algebra, we will get actually x, there we go. So we will get 1 4 0, and then plus t times this column vector here. So t times 0 is 0t, and then t times 2 is 2t, and then t times 1 is t. And so that just simplifies to this or what we wrote here. And this part right here would be our kernel of A. And then, as we mentioned before, that we can write any solution with the um in the form of x is equal to x naught plus y, where y is the kernel of A. This is basically the same as what we have here. So our x naught is equal to 140, and then our y is just equal to some constant. We in the slides it said s, but we are using t, multiplied by y1, 2, and 3, which in this case would be 0, 2, 1. So what we end up getting is a particular solution x naught, and then plus a our kernel, which can be any number, because we said t is any constant, and it will make this systems of equation, or the solution will be true. And to show that the kernel y multiplied by the matrix A is equal to 0, we're just gonna simply multiply A and the kernel. So just gonna do that really quick. This would be -5, 2, -4, and then -1, 2. -1, 2, and then multiplied it by 0, 2. Actually, let's do it here. 0, 2, 1. As you can see here, we have 3 columns and then 3 rows. So we are able to multiply these two matrices. And what we end up is, we do this really quick. We have 0 times 1 plus 2 plus 2 times 2 minus 4 times or 1 times -4. So that would just be 4 minus 4, which would just equal to 0. And then a bottom one would be -5 times 0, 0, plus 2 times -1, which is -2, plus 2 times 1, which is 2. So you have 2 minus 2, and that would just be 0. And this just shows that this this column vector is in the kernel of matrix A. And we just did that by proving that A times Y is equal to 0. And yeah, that's pretty much it with systems of equations. So when it comes with doing these types of problem, it will usually be 1 or 2 cases. The first case would be what we got in the first video, where it just ends nicely with having ones across the diagonal. So that means our x, y, and z have its own number. Or we could have such a case where we have a solution plus a kernel. So that means that we don't get ones across the main diagonal and just ones. So a diagonal matrix. And this will give us a different type of solution that we have to write in terms of the kernel, which would be x equal to x naught plus the kernel of A. Yeah. So yeah, hopefully you enjoyed. Hopefully this video helps with any questions that you had or any process on how to do this. So yeah, I will see you guys in the next video.